So hi, I'm Santo. I'm a professor of informatics. I joined the faculty 1 month ago, but I was a postdoc here many years ago, so it was a nice return. My background is in theoretical physics, and this is one way to tell you this is going to be a boring talk without robots moving around or even eagles catching drones in flight, which is actually a very cool video, by the way, so I apologize for that. This is going to be a talk on network science, and luckily YY has already told you something about that, so of course it's a huge area, very growing. There are many things to do there, and I did various things in there, but today I would like to focus on one of the most active area of investigation here, which is detection and characterization of community structure. I also told you about this. Of course, there is no reason to tell you. You've seen his name as well there, as a potential co-worker for the things that we would like to do in this area here, because, there are many people also here at IU, not only in our department, who are very interested in that. Like, for instance, I mentioned all the sports that was mentioned in the introductory slide as well. So communities are subgraphs, so parts of the networks, in which for some reasons, they are components, the nodes, somehow have much more interaction with each other or relation than with nodes of different parts. So this is a very schematic representation that you see there with these three groups and the colors indicating their respective memberships. And thinking about specific types of networks, for instance, like social networks, they could represent people with common interests, and that's why they have more contacts with each other, or scholars working on the same topic in collaboration networks, or a protein with equal similar function in protein interaction networks, and therefore they interact more closely with each other, or papers on the same related topics in citation networks, and therefore they cite each other more often than they would cite other works. So why should we do that in the first place? You've seen already some applications YY's talk, but there are theoretical reasons for that too. One reason is to infer the organization of the system. It's also much easier to understand if you break it down in pieces, which are more homogeneous. You can classify nodes better if you know the modular structure of any complex system, because then you can, based on your knowledge of where the clusters are, say something about the role that the node may have within its own module. If it's a connector, if it's like staying at the boundary with the other parts of the network and therefore acting as a sort of gateway for the dissemination and diffusion of signals or information, epidemics, or if it's instead well embedded inside, it can help for the problem of missing links, which is a problem related to sampling on networks. Sometimes you don't get to see all the links which are actually there. I don't know. Yeah, maybe. Yes. Yeah, yes, probably better. So missing links is a problem. I mean, if you don't see all the links which are actually there because, your sampling procedure is inaccurate, you don't do the measurements, and therefore you would like to see if there are additional links on top of your collection based on existing information. If you know the modules, with the modules you may also suspect that these missing links are most likely inside the modules than within. And there are important effects on dynamics for the diffusion of signals, for instance, because if the system is strongly clusterized, information and, kind of spreading phenomena slow down. So the basic theoretical questions that we are working on, that all this huge community is working on, it's truly interdisciplinary, by the way, is what is a community? Because it's an ill-defined problem, like all clustering problems. Where does it come from? So models to explain where communities come about. How to detect it, of course, that's what everybody wants to know, to give the tools so that they can apply in your data, and how to validate the methods to detect communities. We've done some works in some of these, pretty much we're just trying to address all these questions. Yeah. So this is a picture showing a model that we propose in which we show that the models, say, social networks based on triadic closure in which people get acquainted through a person that knows them both. So the closed triads this way, that these models automatically kind of spontaneously generate communities. You see the different instances in this case. So this is a method which was introduced for other reasons to increase the so-called local clustering of transitivity property of the networks, but at the same time, they give you for free also community structure. And the other thing we've been very active on is proposing tools and methods to test the methods, to compare the performances to see whether your new method is any good or it's better than existing techniques. This is a picture, a snapshot of a tool that we introduced. It's an artificial network, which is called the LFR benchmark now. It is used, it's become a standard tool in this area, and it's also coded, and there is even a Wikipedia page not written by us, so somebody tells you something about that. And of course, I want to apply this stuff as well in different domains. So social networks, already told you something about that. I also very much like information system. This is a citation network of authors to the brain and also to gene protein networks with some of the people that you've seen listed. And with that, I thank you.